Hello there, wind energy students. Dr. John Schrage here, and it's time to take what we've been learning about the winds at different heights of the atmosphere and the stability of the atmosphere and start trying to come up with what we're going to call wind profiles. That is to say, some kind of explanation as to how the wind is changing with respect to height. You might remember we did like temperature profiles and so on in an earlier module of the course. Now we're doing the same sort of thing with winds. And so these profiles are going to be examples of diagrams in which we're going to be explaining how wind changes with respect to height. And the way to think about it would be like, it's the relationship between height and above ground level and wind speed. I do want to draw your attention to that abbreviation AGL, which your textbook throws in from time to time. It just means above ground level. Okay, so it's just sort of the height above the ground, in contrast to like above sea level or something like that. Now, as I suspect you will already have an intuition about, the wind profile is going to change. There's going to be under different meteorological conditions at different times of day in different parts of the world. The profile of wind speeds with respect to height will be different. And what we're going to be working with first is the so-called log wind profile. Here, log is as in the mathematical sense of logarithm. Not like a tree that's been cut down or something like that. And it turns out that the log wind profile is a pretty good approximation of what the winds are doing, how the wind speeds are changing with respect to height in general. Actually, with no other information, this is not a terrible approximation. We're going to have better approximations if we say, no, we're under certain kinds of weather conditions, or it's at night, or something. But as a general first guess, the log wind profile is actually pretty good. And so we're going to be working with some graphs of the log wind profile. And here we just have two graphs showing the log wind profile. They're both showing the same information, just displayed differently. In both of these graphs, the x-axis is wind speed, which we're using the symbol U for. I'm not loving that, but we'll talk about that in just a little bit. And in both of these graphs, the y-axis is the height above the ground, which we use the symbol Z for height. The only difference between these two graphs is the one on the right is drawn on what we call a semi-log piece of graph paper, and the one on the left is being drawn on just a regular piece of graph paper. See how the one on the right has a logarithmic scale to the graph? Now, if that is not something you are familiar with, about working with like semi-log graph paper or a logarithmic scale, I have put on blue line for you under the handouts, there's a page that's about like, are you not familiar with semi-log paper? And I kind of walk you through a little example and link to some videos and pages online and so on that might help you. And of course, you can always talk to me about it too. So these are the same information being presented both ways. Now, there is a formal way to derive the curve of the log wind profile, and it's not terribly instructive. And then your textbook says, hey, I have a hand-waving kind of derivation of this. And, props to the textbook author for trying that, but honestly, the hand-waving derivation isn't terribly useful either. On the other hand, some of the assumptions he made, it's useful to explain because we kind of can see the results here on the diagram here. We can see that there is a rate of change that is the rate of change of the winds with respect to height. The right word for that is wind shear, how the winds are changing with respect to height. And your textbook is going to use the symbol du/dz for this, like the derivative of the wind speed with respect to height. That makes me a little bit frustrated because he's misusing that. It's not a D, it's a partial U. But okay, I get what he's going for here. Okay, it's bad math, but okay notation. So we're talking about like down near the surface of the Earth on that left diagram here, I can see that the wind speeds are changing quite a lot with respect to height, and our value then of du/dz would be big and positive. Whereas, like, once we get more like 60, 70, 80 meters above the ground, I can see that the winds are changing less the wind speed is changing less with respect to height. It's still positive. The winds are getting stronger with respect to height, but not very much. So du/dz is positive, it's just not very big. So the wind shear is great near the surface, and the wind shear is not so great once you get more than, a few tens of meters up. Okay, not loving the notation here for lots of reasons, partially just due to the fact that, no pun intended, but that's not supposed to be a total derivative, that's a partial derivative, but whatever, okay, it's not calculus, we can deal with that. Even more annoying is the fact that he's using the symbol U to mean wind speed. and not the U component of the wind. You remember the U component is the west to east component of the wind. He suddenly hits chapter 4 and stops doing that. Now he's calling U the wind speed. Fine, as long as we're careful about the notation, we know what we mean. Because don't get me wrong, we could do that too. We could also have said change in the U component of the wind with respect to height. And that would be an interesting thing about changes in like wind direction, like the things we did when we talked about the Ekman spiral and so on. But that's not what we're doing in this chapter. Here we're just talking about wind speed, and he's just sloppily using the symbol U for that. Okay, whatever. It's not that big of a deal as long as we're careful about the notation. But one thing I do want to draw your attention to is all this stuff about the log wind profile. We're only talking about the lowest maybe 100 meters or so of the Earth's atmosphere. We're not even talking about the whole depth of the boundary layer here. We're talking like that surface layer or so on, maybe a little bit of the Ekman layer or so on. We're not really very high above the ground here. But that's okay, because that's where wind turbines are. Okay? The hub height of a typical wind turbine is something like 100 meters. So we're basically talking about the winds that are affecting your weather stations, the winds that are affecting your meteorological masts, and the winds that are affecting your wind power production here when we're talking about the log wind profile. Now again, like I said, your book actually bothers to try to come up with some sort of lazy hand-waving derivation of the log wind profile, and I'm not sure that that's terribly useful. I don't like a lazy derivation of it, and I don't really know, the formal derivation is much more difficult, so what's the point? Instead, let's talk about the results, which is this equation that we have over here on the left. Now, that is the equation of the so-called log wind profile, and like I said, this actually fits real observations of the wind quite well a lot of the time. Now, we're going to find out that under different stability regimes and under different meteorological conditions and so on, other wind profiles might fit better, but this is not terrible. Now, let's just take a look here. On the left-hand side of that equation, we've got a U at parentheses Z. What we're saying here is that U is a function of Z here. So, like, you know, this is the value of U we're getting when we plug in a value of Z. If we want to know the wind at height 50 meters, we'll plug 50 meters in for Z and we'll get U. What's over there on the right-hand side looks like a giant mess, but most of those values are, they're just values we plug in. I mean, like that in the denominator there's that, what looks like a K. It's actually a lowercase Greek kappa. That is a value that is in fluid mechanics called the von Karman constant. And as it happens for gases, it's in general a fluid mechanics thing, like hydraulic fluids and stuff like that. But the value for air turns out to be 0.4. Okay, we can just plug in 0.4 and it doesn't hurt anything. The log wind profile has a value in its equation there that is Z naught. That Z with a little zero is called Z naught. The right name for that property is very cool. It's the aerodynamic roughness length. We're going to learn a lot about aerodynamic roughness length on this module. The idea here is that there is some, if you actually could measure, like with a hot wire anemometer, the winds right near the ground, they're basically zero. And in fact, if you got like a few centimeters above the ground, the wind is basically zero. But at some height, we can't say that anymore. Depending on the surface that we're blowing over and how windy it is and stuff like that, at some height above the ground, we will no longer have the wind speed zero. The theoretical definition then of the aerodynamic roughness length is it's how high above the ground, it's the last height above the ground where you can comfortably say, here the wind is also zero. And it's not really something that we measure, it's actually something we can get from the observations of the wind. What we do, I'm going to just sort of zoom in here on the log wind profile side of the graph there. We don't measure Z naught, the aerodynamic roughness length, but what you do is you take observations of the wind at various heights, like from a meteorological mast or maybe the launch of a weather balloon, and you plot those on that semi-log scale version of the graph there. So you just plot those the winds at different heights up there using those, using your markers there, and you just fit a line to there. Now that can actually be done like statistically with regression, or you can just on your graph paper fit a ruler to it and just draw your line. It's fine. And wherever that line that you just drew crosses the y-axis, that's the value of Z naught, the aerodynamic roughness length. So like in this case, it looks like it's about it's about 2/10 of a meter. Okay, again, if you aren't familiar with how to read the scale on semi-log paper, go look at that page under handouts about semi-log paper. But okay, so basically from that height, in this case it's about 2/10 of a meter, from that height down to the ground, that last 20 centimeters, we're assuming that the wind speed is zero. Now, that's just a number that we need for our log wind profile, and as you see, it's going to pop up all kinds of places in the rest of the course. Aerodynamic roughness length is primarily a property of the surface itself, like how rough the surface is. And your book has a table. It's strangely someplace, I want to say it's in chapter 5 someplace, but I kind of reproduced it there. Just giving you a sense of values that we can use for the aerodynamic roughness length over different surfaces. Like a city has an aerodynamic roughness length of about 1 meter, whereas like grassland has an aerodynamic roughness length of just a few centimeters, and like over the smooth open ocean, the aerodynamic roughness length is just a few, fractions of a millimeter. In a broad sense, if you had no other way to try to figure out what the aerodynamic roughness length is, like for example, if you don't have winds at different heights, that you could use that trick on semi-log paper and draw a line and figure that out, which you'll be doing on the homework, by the way. If nothing else, a good estimate of the aerodynamic roughness length is to look around you at what are the obstacles to the flow, and you would say the aerodynamic roughness length is typically about 1/30th of that height. So like in an urban environment where the typical height of the buildings around you is, let's just say 30 meters to make round numbers here, then the aerodynamic roughness length is going to be approximately 1 meter. And it's going to be fine. It'll be a good enough estimate of the aerodynamic roughness length. There's another parameter in here, in this equation for the log wind profile, that's U star. U star is the so-called friction velocity. Now, we are going to learn more again in the rest of this module and in coming modules about this notion of the friction velocity. But the friction velocity is, it's called a velocity because it has units of velocity, like meters per second. But it is not, nothing is moving at the friction velocity. The friction velocity is a measure of something about the meteorological conditions that we're under right now. It's actually about the production of turbulence in the atmosphere under different conditions. Under some conditions, the atmosphere is very efficient at producing turbulence, the little swirling motions and stuff like that, eddies and so on in the atmosphere. In other meteorological conditions, the atmosphere is not good at that. That's called friction velocity, again, just because it's only velocity because it has units of velocity. It's a number that's going to range from approximately 0 under calm conditions and approximately 1 meter per second in strong winds. There actually is a definition in your book of, like, mathematically how we get to the friction velocity, where it's related to a number called tau. Tau is the Reynolds stress, again, don't get bogged down about this, divided by the density. We're going to get to better understanding of friction velocity later. But think of friction velocity as sort of a number that comes to us from, like, what's going on in the atmosphere right now. Okay? What are like the weather conditions going on? So see how the log wind profile had a number in it that was describing the surface the air is blowing over, Z naught, and it had a number that's about the weather conditions we're experiencing, namely that U star. It also had that kappa in there, which is not terribly helpful. That's basically just saying, and it's air. Our atmosphere is not made of hydraulic fluid. Lovely. Okay, that's not so helpful. So we can make graphs of this in something as simple as like Excel, that we can plot this graph, and I did it here for a range of different values of Z naught, the aerodynamic roughness length. So here I plotted them. Some of them are in, the top one is in just a regular scale, and then the bottom one's on semi-log paper. But they're the same data there. And in both cases there I plotted 3 log wind profiles with different values of Z naught. And so, like, the orange curve is for the smallest value of the roughness length over the smoothest surface, and the green curve there is for the one with the roughest surface. And you can see that the roughness of the surface actually is communicated upward to fairly great heights above the ground. The wind speeds are weaker in the log wind profile at, let's just pick 160 meters above the ground, depending on how rough the surface is. Whether that rough, none of the obstacles to the flow are 160 meters tall, but that roughness, the effect it had on the velocity of the wind down near the surface gets communicated upward. Now we're going to see that that's going to happen by turbulent transfer and all that kind of good stuff, but right off the bat, just our log wind profile itself is showing how the surface's roughness gets communicated upward and results, the rougher the surface is, the slower the winds are even well above the surface at like 160, 180 meters, something like that, which is really getting to be kind of outside the realm of which I would even start thinking about the log wind profile. Anyway, I would get hesitant higher than about 100 meters above the ground. We can play the same game over here with ranges, making some more graphs of the log wind profile using different values of U star. Again, here I just chose the same value of our aerodynamic roughness length Z naught for each of these graphs here, and you can see how under different conditions, again, we don't yet have a great sense of what U star is about, but I'm trying to show you just that it changes the shape of this curve. That under different meteorological conditions, the wind still is weak down near the surface no matter what. In fact, in all these cases, the wind goes to 0 at 1 meter above the ground. But at different meteorological conditions, that can result in rather different wind speeds once you get above the ground, depending on how efficiently the atmosphere is moving momentum around. In other words, how efficiently the atmosphere is producing turbulence. Again, we aren't yet quite there as to what U star all means, but I'm just showing you that this log wind profile, it has parameters we can tune. We can make adjustments to that value of U star or that value of Z naught that make this wind profile slightly different shape that can help us understand and describe the wind profile that we're actually observing right now. Now, as it happens, none of those curves that I showed you there are terribly realistic. It isn't terribly, it doesn't generally make sense that like the value of Z naught, the aerodynamic roughness length, doesn't change, but the value of U star does, or whatever. I mean, by and large, we would want to adjust both of those under different conditions. So, for example, I'm just plotting some data that your book had, where like they gave appropriate values in your text for like U star and Z naught over a particular day over a forest, or on a particular day over a grassland, or on a particular day over open water. And you just see that we get different curves. And are all perfectly valid examples of the log wind profile. They're just under different conditions, but they all are described by the same equation. They have different roughness lengths, they have different rates at which the wind speed is changing with respect to height, that is to say different wind shear. You can see how this becomes a very versatile tool. It describes the wind profile under a surprisingly good range of conditions. It is just an approximation to what the real winds are doing. The real winds, if you have a meteorological mast, or if you launch a weather balloon and you're measuring the winds at different heights of the boundary layer, will never be exactly like this, but they're actually surprisingly good. And this will definitely work best under the conditions under which, they're the assumptions under which is derived. And again, we didn't do the formal derivation because it's just a nightmare, but part of the assumptions that were used to make the log wind profile is that we were assuming that the atmosphere that layer of the atmosphere near the surface was statically neutral. Oh, see why I had to teach you about stability first? I don't know why the book tries to punt stability to the end of the chapter. You kind of need to know about stability now. The log wind profile works best if the boundary layer is statically neutral. It is neither encouraging the motion of air parcels up and down, nor discouraging it. We're going to find out that there's going to be ways we can make changes to the log wind profile if that's not true. But by and large, we will want the boundary layer to be statically neutral, which is not a particularly rare situation. Most of the time, the boundary layer is statically neutral on a sunny day. During the daytime, if it's sunny, by and large, the atmosphere gets well mixed by the production of thermals in the atmosphere, and we get a constant potential temperature with respect to height, and the atmosphere the boundary layer anyway, is statically neutral. So this is actually a set of conditions that's not so exotic. An awful lot of the time, we get winds that are pretty darn close to the log wind profile. Now, when you look at the log wind profile, what's uncomfortable about it is that, well, we don't really measure Z naught. We can maybe compute it, and we don't really measure U star. It's kind of a mess to even figure things out. But it seems like, oh crud, we have to use it depends on things we don't really know. But actually it turns out there's a way to get around that U star problem. We can actually make some changes here. We can take this equation that is the log wind profile over there on the left, and there's a way to do a little derivation, a very simple little derivation, and get it rearranged to the form over there on the right. You're going to do that derivation in the homework, okay? Because as much as I don't like assigning derivations, that one's like 3 steps. It's not that big of a deal. But the derivation is like 3 steps. But what you do with this becomes really, really handy. If you could come up with some value of z naught, which isn't, okay, we don't measure z naught, but we have this trick about using semi-log paper to figure it out, or we could just say, hey, we're talking about grassland or field, we'll look up at a table and see what a value of z naught is. We can come up with that. That's not that big of a deal. Now, if I know at some height above the ground, z1, I have an anemometer and I can measure the wind speed at that height, we'll call that u1. Okay, whether that's on a 2-foot tall instrument tower at a weather station, or that's at 50 meters up on some meteorological mast or whatever, as long as I know the wind at one height, z1, I know the speed of the wind, u1. Well, now look at this equation here. As long as I know u1 and z1, now if I want to know the winds at some height z2, I just plug it in and I'll get u2, the wind speed at that height. What a miracle! Look at that. All I had to do, okay, I had to come up with z naught, but that's not the end of the world. And once I have that, all I need is the winds at one place in the atmosphere, like a 2-meter tall tower. That will be fine, which is what we have at every airport out there. And now I can figure out the winds at any other height I want in the boundary layer, or at least in the layer to whatever extent the log wind profile applies. I can figure out the wind at any other height, and it didn't require that weird U star. When you actually do this tiny little derivation to make this thing work in your homework, you're going to figure out, oh, the U star cancels out. Oh, that's a nifty trick. That gets us around a number of problems. The log winds profile is a totally awesome tool. It gives us ways that if we're willing to make certain assumptions, we can now figure out the wind speed at lots of different heights based on just one cheap and easy observation. We don't need necessarily to be measuring the wind at all these different heights with weather balloons or towers or wind profilers or whatever. Now, of course, the reality is we do need those things because the wind is never going to be exactly the log wind profile, and in fact, sometimes the day and under certain meteorological conditions, it can be way off of the log wind profile. But this gives us a tool to build on. Now, in upcoming lectures, we're going to talk about ways in which we can change the log wind profile to make it more reflective of what is really happening at night or under stormy conditions or, over unusually hot conditions and so on. But for right now, this is a pretty slick tool. All right, let me give you a couple quick questions as we wrap up this lecture about the log wind profile. Here's a graph of a log wind profile just on regular graph paper there under a particular set of conditions of Z naught and U star or whatever, but that's just our graph there. And I've labeled 1, 2, 3, 4 heights in there, A, B, C, D. Now, which of those heights is the wind shear greatest? Make a choice from those 4 options and get a little feedback before you move on to question 2.